Hi students, this is our final video for the solutions to the 2024 HSC Maths Extension 1 exam. In this video we're going to look at questions 13 and 14. 13a. In an experiment, the population of insects P of t was modelled by the logistic differential equation dp dt is equal to p multiplied by 2000 take away p. T is the time in days after the beginning of the experiment. The diagram shows a direction field for this differential equation with the point S representing the initial population. Part 1. Explain why the graph of the solution that passes through the point S cannot pass through the point T. And this is fairly simple, isn't it? Because we can see an asymptote here at y is equal to, or p is equal to 2000. So any solution that passes through S cannot cut through that asymptote. It's going to tend towards p is equal to 2000. Part 2. On the diagram provided, clearly sketch the graph of the solution that passes through the point S. So basically you want to follow these little direction lines and not cross through them if you can, and it's going to head towards that asymptote like this. Part 3. Find the predicted value of the population P of t at which the rate of growth of the population is largest. Now here's the rate of growth of the population. Normally we would just differentiate that and put the second derivative equal to 0 and then figure it out from there. But it's going to be very difficult to find the second derivative because we are in terms of the dependent variable. So instead, dp dt, if you have a look at this, this is a parabola. And it's concave down. So we can use the vertex formula to find this turning point. The vertex formula is x is equal to minus b on 2a. Remember, it's the beginning part of the quadratic formula. But in this case, we don't have x, we have p. b is the coefficient of p, a is the coefficient of p squared. So we have negative 2000 all over 2 times negative 1, which is 1000. And that's the answer. Question 13b, part 1. Show that cos to the power of 4x plus sine to the power of 4x is equal to 1 plus cos squared 2x all over 2. So I'm going to start with the left-hand side. Now this is really close to cos squared x plus sine squared x all squared. If you expand this out, we've got an extra term. And that term is 2 times sine squared x times cos squared x. So all I'm going to do is subtract that term. Sure that makes sense to you. Equals cos squared plus sine squared is 1. Take away 2 sine squared x cos squared x. Now if we have a look here on the right hand side, we can see a cos squared 2x, and that kind of gives us a clue. And this looks really like sine 2x all squared. Now sine 2x all squared is 2 sine x cos x all squared. In other words, 4 sine squared x cos squared x. So we're only out by a factor of 2. So let's multiply top and bottom by 2. And that will give us 1 take away. This numerator here is going to be that sine squared 2x over 2. Making a common denominator, we have 2 take away sine squared 2x all over 2, but we don't want sine squared 2x, we want cos squared 2x. So that's equal to 2 take away 1 minus cos squared 2x in brackets all over 2, which is equal to 2 take away 1 is 1 plus cos squared 2x all over 2, which is equal to the right hand side. 2, hence or otherwise evaluate the integral between 0 and pi and 4 of cos to the power of 4 x plus sine to the power of 4 of x dx. So of course we're going to use what we have just proven. So this is going to be equal to the integral between 0 and pi on 4 of 1 plus cos squared 2x, and I'm going to bring that half out the front, dx. Now we need to use an identity to get rid of this squared. So that's going to be a half integral between 0 and pi on 4 of 1 plus, and using the identity that's up here, we're going to have a half outside of 1 plus cos 4x dx. Tidying it up, half integral between 0 and pi on 4 of 1 plus a half, which is 3 over 2, plus a half of cos 4x dx, which is equal to a half. Let's integrate. We've got 3x on 2 plus a half, and when we integrate cos 4x, we end up with sine 4x divided by 4, and there are our limits. So substituting them in, we've got a half. 3 times pi on 8 plus 1/8 sine of pi, take away, and that'll be 0 plus 0. And what we need to do now is just tidy that up. We have got 3 pi on 16 plus 1 on 16, and sine of pi is 0 actually, isn't it? So 3 pi on 16 is our answer. 13c, the vector A is 1, 3, and the vector B is 2, negative 1. The projection of a vector x onto vector A is equal to Ka. K is a real number, and the projection of vector x onto vector B is Pb, where P is a real number. Find the vector x in terms of K and P. Now we know that the projection of x onto A is going to be A dot x divided by the magnitude of A all squared times vector A. And so this here is going to be equal to K. And ditto, we have projection of x onto B is going to be B dot x over magnitude of B all squared times by vector B, and so just like before, this one here, that is going to be equal to P. So let's work through both of these equations. We'll start up here. Now we've got A dot x will equal K multiplied by the magnitude of A all squared. The magnitude of A is 1 plus 9, which is 10. And then, well, just the square root of 10, sorry, and then squared is just 10. So that gives us one equation. And let's let x have components x1 and x2. That means the dot product is going to be x1 plus 3x2 is equal to 10k, and that's our first equation. Now over here, we've got b dot x is equal to p times the magnitude of b all squared, which is the square root of 5 all squared, which is 5. And again, letting x have components x1 and x2, we have got 2x1 minus x2 is equal to 5p, and that is our second equation. So what we have to do is solve these simultaneously, and we'll start by multiplying this one by 2. That'll give us 2x1 plus 6x2 is equal to 20k. Alright, I'm going to subtract this guy from this one. So that's going to give us 7x2 is equal to 20k minus 5p. So x2 is equal to 20k minus 5p all over 7. Now substituting into this equation here, we get 2x1 take away 20k minus 5p all over 7 is equal to 5p. Multiplying everything by 7. 14x1, watch this negative here, minus 20k plus 5p is equal to 35p. 14x1 is equal to 30p plus 20k. x1 is equal to, let's just turn that around, 20k plus 30p all over 14, which is 10k plus 15p all over 7. D, using the substitution u is equal to e to the x plus 2e to the negative x and considering u squared, find the integral of e to the 3x minus 2e to the x all over 4 plus 8e to the 2x plus e to the 4x dx. All right, we'll start with u is equal to e to the x plus 2e to the negative x and find the derivative du dx, which is equal to e to the x minus 2e to the negative x. So in other words, du is equal to e to the x minus 2e to the negative x dx. Now they've given us a clue. They said consider u squared, which is e to the x plus 2e to the negative x all squared, which is e to the 2x plus 2 times e to the x times 2 times e to the negative x, which is 4, plus 4e to the negative 2x. Now if we have a look at this, it doesn't look anything like that or that. In fact, we've got all positive powers. So I'm going to start this question by doing a really sneaky thing. So instead of having e to the 3x minus 2e to the x all over 4 plus 8e to the 2x plus e to the 4x, I'm going to divide top and bottom by e to the 2x. And I think that's going to end up giving me something that looks more like what we've got there. We have got, let's see, e, take away 2e, e to the x, take away 2e to the negative x, so that's better, all over 4e to the negative 2x plus 8 plus e to the 2x. Okay, I think we're just about ready to substitute in here. So the numerator is that. So that's going to be du. All over. I've got the e to the 2x. I've got the 4e to the negative 2x, but I'm wanting 4, not 8. So would you agree that this is going to be equal to u squared plus 4? Which of course we know how to integrate, don't we? It is going to be inverse tan of u on 2, and we need a half out the front, plus c. So that is equal to a half inverse tan u is e to the x plus 2e to the negative x all over 2 plus c. 14a, find the domain and range of the function that is the solution to the differential equation dy dx is equal to e to the x plus y and whose graph passes through the origin. So we want to solve this differential equation. So I'll start with dy dx is equal to e to the x times e to the y, and we're going to separate the variables. So I'm going to bring this dx up here and the e to the y down there. So we're going to get 1 over e to the y dy equals e to the x dx. Words, e to the negative y dy equals the integral of e to the x dx. So we've got negative e to the negative y is equal to e to the x plus c, and now I need to resolve this constant. We know that it passes through the origin, so when x is equal to 0, y is equal to 0. So we get negative e to the 0 is equal to e to the 0 plus c. So negative 1 is equal to 1 plus c. c is equal to negative 2. Therefore, negative e to the negative y is equal to e to the x minus 2. Now let's make y the subject. So I'll start by taking this negative over. So e to the negative y is equal to 2 minus e to the x. Taking logs of both sides, negative y is equal to ln 2 minus e to the x, and take the negative over. That's not the answer to the question, is it? We want to find the domain and the range. So let's start with domain. We're interested in any values of x, down here, sorry, that are going to result in this being less than 0, because we can't have log of a negative number. So we want 2 minus e to the x to be greater than 0. It can't even be equal to 0. In other words, 2 has to be greater than e to the x. E to the x is less than 2. Taking logs of both sides, x must be less than ln 2. That's the domain. Now we're going to do the range, and that's a little trickier. Now we are looking at a function here that's a negative log function, and then inside these absolute values we've got a negative x thing, because you can see that there. So what's the effect, of those transformations? Like, here's normal log. This negative here will flip it over the x-axis, and this negative here will flip it over the y-axis. Now there's also a 2 happening there, but that's more to do with the domain, so we don't really care about that. What is the effect of all of that on the range? So here's the question. Can this thing here keep going off happily to negative infinity, or does something stop it? In other words, what is the limit as x approaches negative infinity of negative ln 2 take away e to the x? Well, we know e to the negative infinity will approach 0, so this thing is going to approach negative ln 2, and that's the lower bound. So our range is going to be y has to be greater than, it is an asymptote, so because it tends towards there, it's going to be greater than negative ln 2. 14b. For what values of the constant k would the function f of x equals kx over 1 plus x squared plus arctan x have an inverse? Now this is kind of a cool question, because there's no way we're going to get any solution to this by swapping the x and y. If you have a look at it, we would have x is equal to ky over 1 plus y squared plus arc tan y, and there's no way to make y the subject. We're not actually even going to get a mark for doing that. So we've got to think about, what does it mean for a function to have an inverse? Now you may have been taught that a function will have an inverse if it passes the horizontal line test. So for example, this will not have an inverse. In fact, for a function to have an inverse, it has to be monotonically increasing or monotonically decreasing. In other words, always increasing or always decreasing, no turning points. So basically, we have to prove that this function, or show what values of k, will mean that this function is always increasing or decreasing. And that, of course, is the first derivative. And I quite like that, because see this 1 plus x squared here? That's the derivative, or most of the derivative, of arctan x. So let's start by differentiating. Now we have got a quotient rule here. So I have got u is equal to kx and v is equal to 1 plus x squared. So u dashed is equal to k and v dashed is equal to 2x. So we have v, 1 plus x squared, times u dashed minus u times v dashed all over 1 plus x squared all squared. Now let's do that part there. Plus 1 over 1 plus x squared. Let's tidy that up. We end up with k plus kx squared minus 2kx squared, and I'm going to make a common denominator, so plus 1 plus x squared all over 1 plus x squared all squared, which is equal to, what have we got here, kx squared minus 2kx squared, so that's minus kx squared plus x squared plus k plus 1 all over 1 plus x squared squared. And so we want to figure out what values of k are going to make this positive. Now, we note that the denominator is always positive because of this squared, so we only need to solve for the numerator. So let's figure out what values of k are going to make negative kx squared plus x squared plus k plus 1 greater than 0. Factorising the x squared out, we have x squared in brackets 1 minus k plus k plus 1 is greater than 0, and this is a parabola. This is of the form ax squared plus b is greater than 0, which means that for it to look like this and be always positive, we want a greater than 0 and we want b greater than 0. In other words, 1 minus k has to be greater than 0, so k is less than 1, and k plus 1 has to be greater than 0, so k is greater than negative 1. Therefore, the solution to this particular inequality is going to be negative 1 is less than k is less than 1. Now let's look at the other case. Can we find a k where this is always going to be less than 0? So negative kx squared plus x squared plus k plus 1 is less than 0. Again, because this is always positive, we can ignore the denominator. So factorising x squared 1 minus k plus 1, and this time we want it less than 0. So again, we've got a parabola, but this time we want it like this. So we want coefficient of x squared to be less than 0, and we want this to be less than 0 as well. So we've got k is going to be greater than 1, and k plus 1 has to be less than 0, so k has to be less than negative 1. And that's not possible for k to be greater than 1 and less than negative 1, so no solution. So actually, the only answer to this question is what we found on the previous slide. 14c. Explain why the equation inverse tan of 3x plus inverse tan of 10x equals theta, with thetas between negative pi and pi, has exactly one solution. So we're going to do this graphically. And we'll start by graphing the curve inverse tan of x, which looks like this, and it has an asymptote at pi on 2 and another one down here at negative pi on 2. Now, what is the effect of putting a 3 here in front of the x? Do you remember that that is going to make this move towards the y-axis? It's going to make it steeper, and even more so for this one. Still going to stay in that negative pi on 2 to positive pi on 2 range. Now we're going to add those two curves together. This time it is going to go outside that boundary. It's going to come up here and tend towards an asymptote of pi, and then down here towards an asymptote of negative pi, which kind of makes sense. All right, we have graphed y is equal to inverse tan of 3x plus inverse tan of 10x. And we note that it is always increasing or monotonically increasing. It never turns around. All right, we've done that side. Now we need to do this part. Now we're going to graph y, colour am I going to choose? Orange. Y is equal to theta. And y equals theta is a horizontal line. Now, let me just get rid of these two graphs here so you can see what's happening. Wherever I draw a horizontal line in between negative pi and positive pi, it's going to cut that purple line only once, and in fact exactly once. Can you see that? Oops, that's not one there. So this is what we're going to write. Graphically, we can see that there is exactly one point of intersection between the graphs. Between the graphs. This is because y equals inverse tan of 3x plus inverse tan of 10x is monotonically increasing, and y equals theta is horizontal. Therefore, there is exactly one solution to the equation. Inverse tan of 3x plus inverse tan of 10x equals theta. Part 2, solve inverse tan of 3x plus inverse tan of 10x is equal to 3 pi on 4. Right, tricky question. We'll start by taking tan of both sides. And of course, tan of 3 pi on 4 is negative 1. Now, don't make the mistake of thinking you can expand that out. It would be too simple anyway. But this is tan of A plus B. And we know that that's going to be tan A plus tan B all over 1 minus tan A tan B. So we have got tan of inverse tan of 3x plus tan of inverse tan of 10x all over 1 minus tan of inverse tan of 3x times tan inverse tan of 10x is equal to negative 1. We can tidy that up. Tan of inverse tan of 3x is 3x plus tan of inverse tan of 10x is 10x all over 1 take away tan of inverse tan of 3x is 3x and ditto 10x is equal to negative 1. So therefore 3x plus 10x must equal negative 1 plus 30x squared. So we have a quadratic here. We have 30x squared minus 13x minus 1 is equal to 0. We could use the quadratic formula, but we can factorise this. So we've got 1 and 1. Factors of 30, 10 and 3 actually don't work. It's 15 and 2. So 15x and 2x, because I want negative 15x plus 2x. And so x is either equal to negative 1 on 15 or a half. But we just proved in part 1 that there is only going to be one solution. And the best way to figure that out is to substitute them both in. So starting with 1/2 and substituting in, I've got inverse tan of 3 times a half plus inverse tan of 10 times a half, and that is equal to 2.356. So when x is equal to a half, I get theta is equal to 2.356, and 3 times pi divided by 4 is that's what that's equal to. So that's good. Now what happens when I put negative 1 on 15 in? I get inverse tan of 3 times that plus inverse tan of 10 times that. Oops, just made a mistake. Answer bracket. And I get negative, so when x is equal to negative 1/15, I get theta is equal to negative 0.785. And that's not the answer. So our solution is x is equal to a half. 14d. A particle is projected from the origin with initial speed v at an angle of theta to the horizontal. The position vector of the particle, r of t, where t is the time after projection and g is the acceleration due to gravity, is given by r of t is equal to vt cos theta, vt sin theta minus gt squared all over 2. Let d of t be the distance of the particle from the origin at time t, so d of t is equal to the modulus of r of t. Show that for theta is less than inverse sine of root 8 on 9, the distance d of t is increasing for all t greater than 0. So let's start with Pythagoras' theorem, because this particle is projected from the origin, and if we want the distance at any point from the origin, then this part here is going to be y of t, and this is x of t. So d of t all squared is equal to x of t all squared plus y of t all squared, which is equal to v squared t squared cos squared theta plus vt sine theta minus gt squared on 2 all squared, which is equal to v squared t squared cos squared theta plus v squared t squared sine squared theta minus 2 vt sine theta gt squared on 2 plus g squared t to the 4 on 4 equals v squared t squared cos squared theta plus sine squared theta minus, got a couple of t's there, so vg sine theta t cubed plus g squared t to the power of 4 on 4, which is equal to v squared t squared, that's 1, minus vg sine theta t cubed plus g squared t to the power of 4 on 4. Now we want to know when d of t is increasing. So we want d dashed of t greater than 0. It is actually sufficient just to differentiate this and solve it greater than 0, but let's do it the long way. D of t is equal to v squared t squared minus vg sine theta t cubed plus g squared t to the power of 4 on 4 to the power of a half. D dashed of t is equal to a half times v squared t squared minus vg sine theta t cubed plus g squared t to the power of 4 on 4 to the negative a half times by the derivative of the inside function, which is 2v squared t minus 3vg sine theta t squared plus this 4 will come down and wipe that one out, so it's g squared dt cubed, which is equal to 2v squared t minus 3vg sine theta t squared plus g squared t cubed all over 2 times the square root of v squared t squared minus vg sine theta t cubed plus g squared t to the power of 4 on 4. And that denominator is always positive. So we only need to solve the numerator being greater than 0. We have a cubic here, but we can easily factorise a t out. I'm going to turn this around and make this term first. G squared t squared minus 3v gt sine theta plus 2v squared. Now here's a parabola in here. If we want a parabola to be always greater than 0, then we need it to be positive definite. It's going to be positive definite providing the coefficient of t squared is greater than 0, which it is, and the discriminant has to be less than 0. And so our discriminant is b squared minus 4ac, which is 9v squared g squared sine squared theta minus 4 times g squared times 2v squared. And we want that to be less than 0. So 9v squared g squared sine squared theta minus 8v squared g squared. Factorising v squared g squared, we have in brackets 9 sine squared theta minus 8. And so this is going to be less than 0 because that's positive there, providing 9 sine squared theta minus 8 is less than 0. In other words, sine squared theta must be less than 8/9. Now, it means that sine theta has to lie between negative root 8/9 and positive root 8/9. But we know that this is going to be positive because theta is positive. It's the angle that we launched this thing at. So it's between 0 and pi on 2. So therefore, sine theta must be less than root 8/9. Theta has to be less than inverse sine of root 8/9.